Okay, so good morning, everyone. So this is for our second week for chemistry, so stoichiometry. Okay, starting from this module, we will be dealing with a lot of chemical reactions and equations all throughout this course. That is why it is very important that you're equipped with one of the essential tools in chemistry. Stoichiometry is a quantitative study of reactants and products in a chemical reaction. Okay, this will be the focus of this module, but before we delve into the world of chemical reactions, we must first understand several concepts, including atomic mass, the mole, molar mass, and molecular formula. Okay. So again, stoichiometry is the quantitative study of reactants and products in a chemical reaction, so relating to quantity. So these are the learning outcomes for our module for today. Number 1, know how atomic mass of elements are determined. Number 2, understand the concept of Avogadro's number and the mole. Number 3, determine a molecule's compound's molar mass, molecules or compound molar mass. Convert between grams, moles, number of atoms or molecules. Calculate the percent composition by mass or mass percent of each element in a compound. Apply mass percent information to calculate the amount of an element in a given compound. Determine a compound's empirical formula. Determine a compound's molecular formula. Use chemical formulas to write equations representing chemical reactions. Number 10, balance chemical equations. Number 11, understand stoichiometric relationships of entities in a chemical equation. Number 12, determine how much reactants are needed to prepare a known amount of product. Number 13, predict the amount of products formed in a chemical reaction. And number 14, identify a reaction's limiting and excess reactant. Okay, so that those are the learning outcomes to be expected by the end of this module. So first, let's define atomic mass and molecular mass. So atoms are extremely small particles, and an enormous number of atoms is needed for a sample to be visible to the naked eye. The mass of an atom is therefore extremely small that it would be cumbersome to express their masses in grams, so we use the atomic mass instead. The mass of an atom depends on the number of electrons, protons, and neutrons it contains. By international agreement, atomic mass or atomic weight is the mass of the atom in atomic mass units, where 1 AMU is defined as a mass exactly equal to 1/12 of the mass of one carbon-12 atom. So carbon-12 is the carbon isotope that has 6 protons and 6 neutrons. Setting the atomic mass of carbon-12 at 12 atomic mass units provides the standard for measuring the atomic mass of the other elements. Most naturally occurring elements have more than one isotope. So to determine the atomic mass of these elements, we take the average mass of the, by the way, before we proceed to this one, if we take our periodic table, okay, so the atomic mass of the element is the number below the element, okay, this one. So this is what we refer to as carbon 12. All right, so let's go back to the presentation. Most naturally occurring elements have more than one isotope. So to determine the atomic mass of these elements, we take the average mass of the naturally occurring mixture of isotopes. In the case of carbon, the natural abundances of its isotopes are 98.9% for carbon-12 and 1.1% for carbon-13. The atomic mass of carbon-13 has been determined to be 13.00335 atomic mass units. Thus, the average mass of carbon can be calculated as follows. So 12 atomic mass unit for carbon-12 and 98.9% of existing carbons, naturally occurring existing carbons are carbon-12, and then 13.005 atomic mass units for carbon-13, and 1.1% of existing carbons are carbon-13. So taking the average, we have 12.01 atomic mass units. Going back to our periodic table, we can see that the average atomic mass of carbon is 12.01011 atomic mass units. In other words, the atomic mass that we are seeing in the periodic table is the average atomic mass of an element. Okay, let's go back to the presentation. So we have here an example. So gallium, or Ga, has two naturally occurring isotopes. 69 gallium with an atomic mass of 68.926 atomic mass units, and then gallium 69. Gallium 71 with an atomic mass of 70.926 atomic mass units. Percent abundances of the two isotopes are 60.15% and 39.85% respectively. So find the average atomic mass for gallium. Okay, so 60.15% of naturally occurring gallium are gallium 69 with 68.926 atomic mass units, and then 39.85% is gallium 71 with 70.926 atomic mass units. Okay. For the solution, like the other example earlier, so 60.15% times 68.926 atomic mass units, and then 39.85% plus 70.926 atomic mass units. So we get an average atomic mass for gallium as 69.723 atomic mass units. So if we will check on the periodic table, so gallium, so this one. 69.723 atomic mass units. Let's go back to the presentation. Okay, next, Avogadro's number and the mole concept. So the atomic mass unit provides a scale for comparing relative masses of atoms, carbon-12 being the point of reference. However, we deal with macroscopic samples containing enormous number of atoms in reality. So chemists use the fundamental SI unit for amount called a mole. Okay, so we've mentioned it in our first discussion. The SI amount of unit for amount of matter is called a mole. The mole is the amount of substance containing the same number of objects as there are atoms in exactly 12 grams of carbon-12. Okay, so to help you imagine more. So we have carbon-12, okay, 12 grams of this carbon-12. let's say we have this one. This is amounting to 12 grams of carbon 12. Of course, this will be filled with matter inside. So on and so forth. Take a long time. Anyway, so when they tried to measure, going back to the presentation first. Okay, so they tried to measure how many amount of substance can be found in 12 grams of carbon 12. Okay, and then they determined that is equal to times 10 raised to 23. There, this is the number of substance found in 12 grams of carbon 12. Okay, and they call this the Avogadro's. Go back to the presentation. It was named in honor of the Italian scientist Amedeo Avogadro. Again, this is the number of substance in 12 grams of carbon 12. That is Avogadro's number. Okay, let's proceed. By defining a mole in this way, an element's average atomic mass will be identical to its molar mass. So a single atom of carbon 12 has an atomic mass of 12 atomic mass units, and a mole of carbon 12 has a molar mass of exactly 12 grams. Okay. So how many moles of, we have here another example. How many moles of zinc is in a 12-gram sample? So to convert the given mass of moles, we will be using the molar mass. Okay, so the molar mass is equal to its atomic mass. So we will locate first the atomic mass in the what we call this periodic table. So we will look for zinc in the periodic table. So zinc, Zn, this one. Okay. So the molar mass of zinc is 65.38. Okay, 65.38. Let's go back to the presentation. So the number used here is 65.39. So anyway, there is a lot of this rounding off in these numbers. So you may notice that these are not exactly the same with each other. Sometimes there is a 1 decimal point that differs. Okay. So anyway, we're trying to look for the number of moles in 12 grams of zinc. So we have here 12 grams of zinc times from the atomic mass. Okay. Why is this so? Because let's transfer this one to the Jamboard. Let's solve this on the Jamboard. Okay. I'll delete this one. Okay, so we have 12 grams of zinc times. Okay. From the periodic table of elements, we found that the atomic mass unit of zinc is 65.38, but in the example they use 65.39. Okay. So that is for the atomic mass. The unit of atomic mass is actually grams per mole. Okay, grams per mole. Now, this is grams, so we're looking for the number of moles, right? So we need to cancel grams and be left with moles. So we will place 65.39 in the bottom part. Okay, grams per mole. So what will happen to the mole is, this is zinc. What will happen to the mole? Of course, it will go up. Remember the rule on fractions? When we have a fraction on the denominator of that fraction will go up. So we will have here 1 mole of zinc okay, over 65.39. 39 grams of zinc. That's why the equation from our example look that way. So we will cancel grams. Okay, we will cancel grams. So we will now be left with moles. And the answer was so divided by 65.39 will be equal to 0.1835. That's for the number of moles. Okay. So I'll go back to the presentation now. Kasi yung use 0.22. Okay. Let's proceed. For the molecular mass, okay, I'll go back to it. Atomic mass is for an atom of an element, of course. For molecular mass, then this is for a molecule. Again, the definition of molecule is when 2 or more atoms are joined together, regardless of if the atoms are different or the same. Okay, so the molecular mass or molecular weight is the sum of the atomic masses in the molecule. To get the molecular mass, we need to multiply the atomic mass of each element by the number of atoms that element present in the molecule and take the summation. For example, the molecular mass of silicon dioxide or SiO2 is, okay, so in SiO2 we have 1 silicon atom and then 2 oxygen atoms. Okay, so silicon plus 2 oxygen. Silicon, we will check on our periodic table. Silicon has 28.086 for the atomic mass, and then oxygen is 15.999 or 16. So again, silicon 28.086, oxygen 15.999. total or number. I'll delete this one. Delete this one. SiO2. Okay. Molecular mass. So this is made up of 1 silicon and 2 oxygen. Okay, 2 oxygen. Again, silicon was 28.086 EMU. Plus oxygen is 16. So we have 2 oxygen atoms, so 2 times. So this will be multiplied by 2. Okay. 6 plus 2. 60.06. Okay. So this is the molecular mass of silicon dioxide. I'll go back to the presentation. Okay, let's proceed. Find the molecular mass. From the molecular mass, we can determine the molar mass of a molecule or compound. The molar mass of a compound in grams is numerically equal to its molecular mass in atomic mass unit. Therefore, the molar mass of silicon dioxide is 60.09 grams. Now that we know that this relationship, we can now calculate the number of moles in and individual atoms in a given quantity of a compound. Okay, so let's have this next example. So glucose is a simple sugar with a molecular formula C6H12O6. In 50 grams of glucose, calculate for 1, the number of moles of glucose, the number of molecules of glucose, and the number of atoms of oxygen in the sample. Okay, so let's solve this one. So the first step is to solve for the molar mass. Okay. Let's do this on the Jamboard so you can imagine it better. C6H12O6. Right. C6H12O6, 50 grams. So these are the given quantities. We're looking for the moles of glucose, the number of molecules of glucose, then the number of atoms of oxygen in the sample. Okay. Moles, molecules, number of atoms of oxygen. We're looking for given 50 grams. C, number of oxygen atoms. oxygen. Okay, let's start with letter A. So the number of moles of glucose. Of course, the first step will be to solve first for the molecular or rather molar mass. Okay, letter A. We have 6 carbon atoms, 12 6 carbon atoms, 12 plus 6. Okay. So from the periodic table, we will look for carbon, hydrogen, and then oxygen. So carbon is 12.011, oxygen is 15.99, and then hydrogen is 1.008. So again, hydrogen 1.008, carbon 12.011, oxygen is 16. Okay. So this will be 6 times 4.01 plus 12 times 1 plus times 3. This is for the molar mass. So let's solve using our calculator. So 6 times 12.011 plus 12 times 1.008 plus 6 times 16. So 180.162. Or let's just use 180.16. This is the molar mass. Right? So this is just the first step. Okay. So the next step is to solve for the number of moles of glucose. Okay. So for the number of moles, you are given the mass. You still see this one. You are given the mass, which is 50 grams, just like our example earlier. So we have 50 grams. So 50 grams glucose times we discussed earlier. So this atomic mass unit will become grams per mole. Okay, and then the mole will transpose 1 mole. And then 180.162 grams. The grams will cancel, so we will be left with 50 divided by 180.162, 0.2775. This is for letter A. The number of moles. Okay, so let's check if we're doing the right thing. Let's go back to our presentation. So our answer for letter A is the number of moles is 0.2775 moles. Okay, so we're on the right process. So the answer here is 0.278. So they rounded it off, but we're using 0.2775 so far. Okay, so the next question is the number of molecules of glucose. Okay, for the number of molecules, whenever we are asked for the number of molecules, this time we will be using the Avogadro's number. Okay, so for the number of molecules, we have we'll be using the number of moles. Okay, 0.27 0.2775 moles, okay, times so this can also be interchanged just like our grams per mole. We'll be using the Avogadro's number. So this is 6.033. Let's cheap. I forgot the value. 6.02. What's the original value again? 6.022. Okay, 1367. So let's use the 6.02 since the module use 6.02. 6.02 times 10 raised to 23 molecules. Per mole. So this is the very definition of Avogadro's number. Okay, so we have the Avogadro's number of molecules per mole of a substance. Okay, space crisis. So upon multiplication, we will have 0.2775 times 6.02 times 10 raised to 23 equal to 1.67. 1.67 times 10 raised to 23 amount of molecules. Molecules meaning this is already the combination of C6H12 and O6. Let's go back to the presentation. Okay. So we have 1.627 times 10 raised to 23 number of molecules. Usually, when we use Avogadro's number, we don't represent it with the unit because it is just the count of the number of substance or molecules or atoms. Okay. In our last question, which is the number of oxygen atoms. So we just multiply it with. Okay. So for letter C, so from the number of molecules of glucose, so 1.67 10 raised to 23 molecules of glucose so times, okay, we have in every molecule of glucose, in one molecule of glucose, we have 6 atoms of oxygen. Okay. If you're wondering where did the 6 came from, it's from the molecular formula C6H12O6. So in one molecule, this is one molecule, C6H12O6. Okay. In one molecule of glucose, we have 6 atoms of oxygen. That's why this formula looks like this. Then the molecules will cancel. Molecules will cancel. We will be left with 1.67 times 6. 10.02 number of atoms of 10 raised to 23 space crisis. So 10.02 times 10 raised to 23 atoms of oxygen. So let's review the process that we did for our solution to this problem. Let's put this one. Okay. So we are given again 50 grams of glucose, and the molecular formula of glucose is C6H12O6. And they're asked to find letter A, the number of moles of glucose, letter B, the number of molecules, and then letter C, the number of oxygen atoms. So for letter A, the first step that we did is we looked for the atomic mass of the molecule. Okay. So to find the atomic mass of a molecule, you just add the atomic masses of all of the elements that make up the molecule. So we have 6 carbons, 12 hydrogens, 6 oxygen. Okay. Adding all of their atomic masses resulted to 180.162 atomic mass unit. And then again, atomic mass unit is equals to grams per mole. So in order to find for the number of moles of glucose or the number of substance, okay, so we multiplied the given 50 grams of glucose to its the inverse of the atomic mass unit in order for us to cancel the grams. Okay, so 1 mole per 180.162 grams of glucose. So we got 0.2775 moles of glucose. Right? And then letter B, for the number of molecules of glucose, we use the number of moles and multiplied it to the Avogadro's number to know the number of molecules. Again, take note of the units that are being cancelled in here. Okay. So if you are looking for moles and you're given the number of molecules, you can still use Avogadro's number, but we will just invert the fraction. Inverse the fraction. Okay. Next, letter C for the number of oxygen atoms. So from the number of molecules of the compound, the given compound, okay, we multiply the ratio of the molecule to the number of oxygen atoms. Again, from the molecular formula, we have 6 oxygen atoms per 1 molecule. Okay, so it resulted to 10.02 times 10 raised to 23 atoms of oxygen. Okay? I guess I'll give you some moment to absorb. 10 seconds. All right, so that's the definition of our 10 seconds. So anyway, let's go back to the presentation. So we have another example in here. So this time we have paracetamol. Paracetamol or acetaminophen is a drug used to treat pain and fever. So its molecular formula is C8H9NO2. Determine the number of carbon atoms in 500 grams of paracetamol. As in the previous example, so we first calculate for the molar mass. So this will be the same steps as we did earlier. We're looking for the number of carbon atoms. Okay, we can solve this using our Jamboard. We'll go back to the Jamboard. Okay, so given our, this again, paracetamol, so C8H9 and O2. Is right? I'll go back to the presentation to check. So C8H9 and O2. Then we'll go back to the Jamboard. 500 grams is given. So this is paracetamol. This is the molecular formula of our paracetamol. So given 500 grams. We're looking for the number of atoms in 500 grams of paracetamol. In order to find the number of carbon atoms, again, we need to find the number of molecules. And then, in order to find the number of molecules, we need to find the number of moles of paracetamol in 500 grams. Okay. And then, in order to find the number of moles, we need to find first the atomic mass of this molecule. Okay. So let's start with the molar mass. Start with the molar mass. We have 8 carbons plus 9 hydrogen plus 1 nitrogen plus 2 oxygen atoms. Okay, so this will be equal to, remember, the atomic mass of carbon is 12.011 plus 9 times. For hydrogen, we have 1.008. Or nitrogen. So this is the new one. We will check nitrogen on our periodic table. Nitrogen. So this is nitrogen 14.007. Okay. So 14.007. We only have one atom of nitrogen, so we have no multiplier. And then for oxygen, we have 16. All right. So we will add this. Let's solve using our calculators. Using our calculators. So 8 times 12.011 plus 9 times 1.008 plus 14.007 plus 2 times 16. We have 1.167 atomic mass unit, or let's go with grams per mole. Grams per mole paracetamol. The next step is to look for the number of moles. Okay, for the number of moles, we will be using our given mass, which is 500 grams, times our atomic or our molar mass. Okay. So again, we will be canceling grams. So we'll place this in the denominator. So 151.167 grams 1 mole. Okay. So equal to, again, this is paracetamol. $500 grams times 1 over 151.167 grams, or 500 divided by 151.167. We have 3.3. 3.3 0 of, this is the number of moles in 500 grams of paracetamol. I'll move this one. Okay, next, after solving for the number of moles, we will look for the number of right. The number of molecules, we have our number of moles, which is 3.3 0.76 moles times Avogadro's number, which is again 6.02 times 10 raised to 23 per mole. Okay. We take note of the units that will be cancelled. So most will be cancelled. We will have 3.3076 times 6.02 raised to 23. Okay. So we have 1.99. Let's just go with 2. 24 molecules. Molecules paracetamol. And lastly, take note of the steps that we did. First, we solved for the molar mass, then the number of moles, and then the number of molecules. So lastly, we will solve for the number of carbon atoms. We'll be using the number of molecules that we have solved earlier. So we have 2 raised to 24 molecules of paracetamol times. So we have 1 molecule of paracetamol. And then in every molecule of paracetamol, we have 8 space bases. Okay. So the unit of this is molecules. We'll cancel the molecules. We will be left with carbon atoms. So this will be equal to 16 times 10 raised to 24 carbon atoms. Okay, so we just repeated the steps of our earlier example. Let's go back. Again, the first step is to solve for the molar mass, then the number of moles, okay, and then the number of molecules. Lastly, the number of carbon atoms. Okay. Again, I'll give you 10 seconds to absorb. Right? So we're good. Let's go back to our presentation. Oh, we have a mistake. I'll check on the Jamboard. The answer should be 160, but we have 16. Okay, gets. Okay, please don't be confused why our answer is different from the answer of the presentation. In the presentation, the answer is 160, but the exponent of the, what you call this? Exponent of 10 is 23, ours is 24. That's why we have 16 and they have 160. It's still the same, still equal. Okay, so ours is not wrong. So 160 times 10 raised to 23 carbon atoms, or 16 times 10 raised to 24 is still the same. Okay? So let's proceed. So next we have formula mass. In the case of ionic compounds that do not contain discrete molecular units, the term for formula mass is used instead of molecular mass. For example, NaCl, or our table salt. Okay? So the formula unit NaCl consists of one sodium positive ion or cation, and then one chlorine anion or negative ion. The formula mass of NaCl is the mass of one formula unit. Okay. So Na is 22.99, Cl is 35.45. So the molar mass of NaCl is 58.54 grams. Okay. So it's just the same. What it's just trying to say is that usually in ionic compounds there's no multiple atoms in a formula. Okay. Usually ionic compounds is straightforward. So next we have percent composition of compounds. So the percent composition by mass, or simply mass percent, is the percent by mass of each element in a compound. So mathematically, we're just trying to get the percentage of the molar mass of an element. So it will be the same, just like what we did earlier. First, we find the molar mass of the molecule, and then we just use it as a denominator to divide on the mass of each component element. Okay, and then express it in percentage. So in this example, our glucose, which is C6H12O6, As we've solved earlier, the atomic mass is 180.24. We just in the percent carbon, so you have you call this 6 atoms of carbon, so 12.01 grams molar mass for carbon, okay, and then 180.24 molar mass for the glucose. So in a glucose, so the composition is 40% carbon, as we can see, through their molar mass, 6.7% hydrogen, and then 53.3% oxygen. So the heavier the element, it takes up most of the mass of the compound or the molecule. Okay. We would arrive at the same results if we use the empirical formula of glucose, which is CH2O. Anyway, example number 5. Find the empirical formula of ibuprofen with percent composition: 75.69% carbon, 8.80% hydrogen, and 15.51% oxygen. So ibuprofen or paracetamol, I think we solved this earlier, but we will try here to look for its empirical formula. So a recap, empirical formula is the simplified molecular formula. Okay. When we say simplified, go to the Jamboard. I'll delete this one. I hope you've taken a screenshot already. When we say simplified, for example, you have C8H12. I notice that this can still be simplified. Okay. These are both divisible by 4. So C4, C2H3. If we divide each component by 4, the difference is, this is the molecular formula. This is the empirical. Just a recap. Let's go back to the presentation. Find the empirical formula of ibuprofen with percent composition: 75.69% carbon, 8.8% hydrogen, and 15.51% oxygen. Okay. So for the solution, the safest way is to assume a 100-gram sample since the mass is not given. Okay. So if we have a 100-gram sample, the 75.69% will be 75.69 grams. 8.8% will be 8.8 grams, and then 15.51% will be 15.51 grams. Using their molar mass, we can now calculate for the moles of each element. Okay. Each element. Again, each element. So in a 100-gram sample of ibuprofen, we have 75.69 grams of carbon. And then the atomic mass of carbon is 12.01. So we will have 6.3 moles of carbon. Same with hydrogen, 8.71 moles. And then oxygen, 0.97 moles. Based on this ratio, we arrive at the formula C6.3, H 8.71, and O 0.97. But notice that all of our chemical formulas are in whole numbers. There are no decimals. So the first step that we can do is to divide all of the subscript with the smallest number. Okay. In this example, C6.3, H 8.71 is O 0.97. The smallest number is 0.97. So if we divide each of them with 0.97, we arrive at C, 6.5, H, 9 or 8.98, but we can round it up to 9, and then O, 1. Okay, but this gives us C, 6.5, H, 9, O, 1. Again, there should be no decimal, but we still have 6.5. This cannot be rounded off. This is so far. Okay. You can round it off if it's near like 8.98. So in order to make this a whole number, we should think of a way, okay, how to make 6.5 a whole number. In order to do that, we should try different factors. Okay. Try first multiply it by 2, multiply it by 3, by 4, or by 5. Try to multiply it with the smallest number possible until we get a whole number. In the case of 6.5, if we multiply it by 2, it will become 13. So that's a whole number. Okay, so we will use 2. We multiply 6.5 by 2, so it becomes 13. Of course, what you multiply to one of the component should be multiplied to the other components as well. So multiplied by 2, 13, multiplied by 2, 18, multiplied by 2, we have 2. So the empirical formula for ibuprofen is C13H18O2. Okay. Right. So that's our 10 seconds. Let's proceed. From the percent composition by mass, we can only get the empirical formula of a compound since subscripts are always reduced to the smallest whole numbers. Always remember that. An empirical formula tells us the relative amounts of each element in a compound. The actual molecular formula could be the same as the empirical formula or its integral multiple, like what we've mentioned in the Jamboard earlier, the difference between molecular formula and empirical formula. To determine the actual molecular formula, we have to know the approximate molar mass of the compound. Example number 6. Eugenol gives the distinct aroma of cloves. So analysis of 2-gram sample shows that it contains 1.46 grams carbon, 0.15 grams hydrogen, and 0.39 grams oxygen. Independent analysis shows that eugenol has a molar mass of 164.22 grams molar mass. Okay. Find its molecular formula. So solution. The total mass of carbon, hydrogen, and oxygen is the same as the mass of the sample. This implies that eugenol contains only these elements. Okay. So first we have to convert the masses of the elements to moles. Again, we are given earlier 1.46 grams of carbon, 0.15 grams of hydrogen, and then 0.39 grams of oxygen. Converting it to moles, we have 0.122 moles of carbon, 0.149 moles of hydrogen, and 0.024 moles of oxygen. Okay, this gives us the formula C 0.12, H 0.15, and O 0.02. Again, divide by the smallest number. So the smallest number in this case is 0.02, but in the solution here, they use 0.024. Just a tip, by the way, when we're doing solving, in the middle of the process, it is recommended not to round off yet. Okay. If possible, do the rounding off of values only on the final answer. Okay. In the middle of the process, don't do as much as possible. Don't do rounding off. Like in this one. Although it was mentioned in the formula that it is 0.02, but in the solution, it used the actual value, which is 0.024. Okay. So again, in the middle of the solution, don't round off yet. So here we got carbon 5.07, hydrogen 6.09, oxygen is 1. This is plausible to be rounded off. So we will have 6.5, H6, and then O1. C5H6O1. Okay? So the apparent molar mass of this is, if we will take the molar mass of this empirical formula C5H6O1, we will have 82.11 grams per mole. Okay, so again, 5 carbon atoms, 6 hydrogen atoms, 1 oxygen atom. So 82.11 grams per mole. The given molar mass in the problem earlier, I'll go back a few slides. Okay, so the given molar mass of eugenol is 164.22 grams. But here, after finding the empirical formula, the molar mass is 82.11, so it does not match. Okay? Meaning, the actual molecular formula of eugenol is not the empirical formula. Okay? It is an factor. It is an integral factor of the empirical. So, when we divide the given molar mass or the actual molar mass by the apparent, when we say apparent molar mass, this is the molar mass of the empirical formula. Okay? So, whatever is the result of the division of the actual and the apparent, this will be a factor that will be multiplied to the empirical formula. So in this case, we have 2. So we will multiply the 2 to each components. Okay? So the actual molecular formula for eugenol is C10H12O2. Okay? So 5 times 2, 6 times 2, 1 times 2. All right. 10 seconds again. Okay. So chemical reactions and chemical equations. A chemical reaction is a process in which a substance or substances is transformed into one or more new substances. To represent chemical reactions in a concise and universally recognized manner, we use chemical equations. So a chemical equation uses chemical symbols to show what happens during a chemical reaction. To illustrate, let us take a look at the chemical equation for combustion of ethane, CH4. When ethane is burned, it reacts with oxygen to produce carbon dioxide and water. Okay, so we have ethane, oxygen gas for combustion. The result is carbon dioxide and water. Symbolically, we will represent this reaction as, again, ethane, oxygen gas. Oxygen gas is always involved when the process is combustion. The result is carbon dioxide. Always, when there is a combustion process, there will always be carbon dioxide as a result. And then water. In this case, there is water because of the nature of ethane. Okay. The plus sign means reacts with. Okay. And then the underlined numbers are the stoichiometric coefficients. The left side of the arrow are the reactants. Okay, so these were the original formula, original molecules that have reacted, and then on the right side is the products of the reaction. Okay, so again, ethane plus oxygen gas, combustion products are carbon dioxide and water. The physical states of reaction species are also commonly stated in parentheses after the chemical symbols. To indicate the physical state, S is used to denote solids, L for liquids, G for gases, and AQ for aqueous solutions. I forgot the definition of aqueous. I'll cheat here. Aqueous means aqueous. So aqueous contains water. Okay. So aqueous is a water-based solution. Again, S for solid, L for liquids, G for gases, and then AQ or aqueous solutions. Example of aqueous is, for example, when we have a reaction and then on the result we have a solution where there is something is diluted in water, so that is an aqueous solution. Balancing chemical equations. Before we proceed to balancing chemical equations, it is important to review first the law of conservation of mass and Dalton's atomic theory. The law of conservation of mass states that mass is an isolated system, is neither created nor destroyed by chemical reactions or physical transformations. This discovery of Antoine led to many new findings, one of which is John Dalton's hypothesis for the existence of atoms. I'd rather not say the name than say it wrongly. The important line here is the law of conservation of mass, that mass is in an isolated system is neither created nor destroyed. Okay? Mass is always conserved. In a chemical reaction, the elements making up compounds rearrange to make new compounds. The atoms making up these compounds, however, are not destroyed, nor are new atoms created. Okay? This means that for every element present in the reactants, an equal amount of element must be present in the products. Okay? So no matter how many elements is found in the reactants, that same number of elements must be found in the products always. Right? Let us account for all the atoms in the unbalanced equations below. So we have CH4. This is ethane, right, as mentioned earlier. And then we have oxygen gas, O2. The result is carbon dioxide and then water. If we count carbon here, we have CC1 carbon. Hydrogen, we have 4 carbons on the left. We only have 2 carbons on the right. So this is not equal. On oxygen, we have 2 oxygen on the left and 3 oxygen on the right. So this is not equal. For a chemical equation to be balanced, the number of elements on both sides should always be equal. Okay? So this is the counting earlier. We can see that the number of atoms of hydrogen and oxygen are not conserved in the chemical equation above. The reaction is unbalanced. To balance it, we need to add coefficients to the reaction species. Okay? By coefficient, we mean multipliers like this one. If we multiply oxygen gas by 2 and then multiply H2O by 2, we now have 1 carbon, 4 hydrogen, 2 times 2, 4 hydrogen, 2 times 2, 4 oxygen, 2 plus 2, 4 oxygen. So the chemical equation is now balanced. Okay? In the case of chemical balancing of chemical equations, there is actually there's a step in here, but we're running out of time. Okay, so I guess this is all for now.